So I thought maybe a good place for us to start, seeing as I've talked about this idea of a hash function, and I didn't really explain what it really is other than the high-level view of it. Let me define what a hash function is. So let's talk about that. So just remember that the idea of the hash function is that it should be able to be taking in a key and it gives me a position in the table. That's what the hash function does. That's the end goal. So it tells me where the record will be or where it should be. That's the ideal thing under the presumption that there are no collisions. So we haven't yet talked about what we do with collisions, but that's a whole other matter. So let's talk about what a hash function is. So I must stress, like I was talking about near the beginning of our discussion about hashing, that keys can be of any type. When I say any, I mean the most generous way of saying this. Not like, oh, I'm looking for some contrived thing that doesn't really make any sense in any reasonable way. I'm just saying that these are things that you're used to seeing. So for example, integer, it could be an integer, it could be a string, it could be a character, it may even be more complex type like an array, it may be an object. The thing is that the hash function has a key that you use to process the function itself, right, as input. So here's our definition of a hash function. So here we go. So I must assure you that this is probably one of the more abstract things we'll talk about here. So after this, I'll be talking more about algorithmic things we can do for our hash table. So we'll start talking about collision resolution and how exactly we can build the hash table. So just if you're looking at this like, damn, this is again a little abstract for me, just hold on. I will give you reasons to why this really matters. So there's two elements to a hash function. So let me just define what a hash function is. So suppose it's a function h that takes in a key and it's actually composed of two functions, f of g of key. So that's what this is, where it has two parts. So it has two parts. So the first one is a hash code. This is what we call the hash code. And the other part will be what we call the compression map. So the compression map, there's two elements to this. So let me define each one here for you. So hash code is just simply a function. It's g of key. So it's just the function g. It takes as input a key that produces an integer. That's all it is. That's all the hash code is. Now, one important practical note that you should if we want like something like the uniformity assumption, or at least something that will capture something of that sort, I just want to mention that a note that we would like the output of G to be large. Why? Because we want to spread the keys uniformly across the table, or even if we can't necessarily do that with our hash code, it may be a very poor hash code, it at least will make sure that we can reach all of the slots in the table. That's one big element of this, is if we don't have this, you're going to have all of your records just constrained at the top of the table or something like that. So that's the first thing. Now next we have the compression map. So this is going to be a function. So this is just another function I'll call it f. It takes an integer, so you can see where it gets the integer from. It gets it from here, right? Hence why we have this as its definition. It gets the integer, so it gets an integer as input, and it maps it to a position in the table, so one of the slots in the table. So just in plain language, it takes in an integer and it outputs a position in the table. That's all this function does. So that's what a compression map is. Very often all this is applying the modulus operator, say like modulo m, where capital M is the size of the table. That's something as simple as that can work as a compression map. So you'll see very often that this is almost like an implicit step. So this is what a hash function is. I thought it would be a good idea we talk about how we can design the hash code then, because you'd see that the compression map is not really as interesting for our conversation here. But let's talk about designing a hash code. At least let's think about this from more of a simpler level. So we're going to think about a simple way we can develop a hash code. We'll talk a little bit about practical effectiveness here. So I thought it would be a good idea we kind of keep things simple here. So I must stress, as I said, it's possible that the key might be a string. But remember, the hash code takes in the key and it produces an integer. So that means we need some way to convert some type that we have to an integer. That's kind of critical for this whole thing to work. Because once you get that integer, you can map it into a slot as per the compression map. So what you can do if given a string, convert it to an integer. So there's several ways you can do this, and this will play an integral role in how the hash code gets computed. If we're thinking about this in terms of strings, because I must stress, I really must stress this, when your key is not an integer, this development of the hash code can make or break the effectiveness of your hash table, or the hash function specifically. If you really do not consider this process careful for your data that you're interested in. So convert this to an integer. So one tool that you can use is use the concept of casting. So if you've never heard of the phrase casting before, that just simply means I take one type and I transform it into another type. So when I transform it, it's just a matter of just reinterpreting it in terms of the other type. And strings are comprised of characters, so symbols. Cast each character to an integer. So you can do this in all sorts of different languages. So I'll have in the notes some examples of how you might do this. I know in the notes that are available to you, you can get access to it. Has an example using Java. So you could just simply use an at function. So very often the string class or a string object will have access for an at function, so you can get a character at a position. Then once you have that, you just perform a casting. So for example, if I got a character, say if I were to do something like this, so char C, I assign it to be S. Suppose I have a string S, call it S, at some position I. This will give me a character. And then secondly, all I have to do now is I could just take and cast it to be an integer like this. So suppose I want to get a value, so I'm going to call it value. To perform casting, you just put parentheses around the name of the type, and you apply it to the given variable of that type. So there's a natural relationship that integer or type int has with char or character. There's a natural relationship that translates over what we call ASCII values. You may have heard of this idea. If you're curious about this, look up the concept of an ASCII table. For each character, there will be a corresponding integer. So if you have characters like these, they can translate each to an integer. Very nice, right? So if you're curious what that is, just here. So just look up ASCII. So I thought probably a good idea now that we have this idea of how we can build we can get a string, we can get values from the string. I thought it would be a good idea we start talking about how we can design a hash code. Now, I'm not claiming these to be perfect in any way, that they don't give you collisions. They most certainly can. So I thought it'd be a good idea we just start thinking about how we would come up with a hash code that tries to improve upon issues that we may have if we get collisions. So I thought we would start off with one of the more basic things you can try to make a hash code, and we'll see what we can think about this. So consider this a first attempt. So this is like the first thing you may try doing after I just described what we had here. So we know we can take each one of the characters and convert them to an integer. Well, one of the first things you might try doing is as follows. So here's first idea for a hash code. So suppose you have each one of the characters. I'm just going to index them in backwards. This will become a little more relevant later. Suppose I give you a string with characters like this. So suppose that to get the integer, what I do is I sum over each one of the positions in this string. I cast each one from its character value. So I grab each one of the characters, I cast it to an integer, and I add this to a running total. So you can implement this with a very simple for loop. So you just take what I wrote over there, you put it inside of a for loop. So your position I is just what you're iterating over from 0 all the way up to, and including k minus 1. So this is the first attempt for a hash code. So this is indeed a hash code. It will give you an integer. There's nothing inherently wrong with this as a concept of a hash code, but this is in fact a hash code because it takes in our key and it returns back an integer, right? So let's think about this. Is this an effective, and I'm not saying like efficient or effective, like keep in mind this is, if k is a constant here, computing this takes constant time, right? Otherwise it takes big O of k time. I'll let you think about that. Is this gonna do very well? Suppose I give you a dictionary that has a lot of arbitrary English words in them. It's probably not gonna do very well. Or it's gonna have issues. There are issues that with this hash code. And I want you to think about these carefully. So the first one is when you sum over values like this, they may not necessarily produce very large values. That's the first issue. When you add them up, because remember, these codes, when you convert them to integers, they're going to be on the order of maybe like 55, 60, nothing like around maybe 80 or 90, but that's not big. If your table, say for example, has 15,000 slots in it, or 50,000 slots in it, keep in mind you can make these hash tables quite big. If you have lots of memory, you can go right ahead and do that if you'd like. It depends. Like I said, these are considerations you would have to make for your given application. But it may be the case that it produces small values, which that's a problem, right? It means you're not utilizing the whole table. It produces smaller integer values. Now, there's another more fatal issue with this hash code. Does anybody see anything that you can point at and say, like, this is not going to cut it? Suppose I gave you an arbitrary English dictionary. An English dictionary may have tens of thousands of words in it. So let's think about it. Let's think about it. Suppose that I had a word like cat. Suppose I have a word cat. Well, each one of these will have a character value, and it all would be part of this sum for that given string if I fed this to G. Well, if I have each one of them, we'll notice very quickly that this gives me some value, right? But notice that if I give you the word tack instead, or act, well, let's think about this. For each one of those, notice that this has the value t, so it's going to have the same value here that's contributed to that sum. It's going to have an a in it, right? Because the a is right here. And a c is right here, right? So tack, if you actually look at it when you go through this process, it's just going to add up to the same value. Likewise, the same thing is going to happen with the word act. I can do even better than this. But this is the fatal issue with this hash code. This is not going to work very well if you have general words. You're going to end up with collisions whenever you have an ordering of characters that happen to have the same characters in them. So it ignores the order of characters. It's going to be a bit of a problem. So let me show you how bad this can get. So this is not by any means the worst example, but I'm going to show you that it isn't just simply 3 words. You can take something as simple as the word stop and get the following. So for example, the word stop, you can also rearrange it to get the word pots. You can also get the word tops. You can also get the word spot. And all of these have the same value. So if you have a general dictionary where you may have it where words are appearing very often, heck, you can even think of our example earlier on where we had, say, the student numbers. Well, there's going to be a lot of possible ways you can get the exact same value for a student number or student ID with the same sets of symbols. In that case, was numeric digits. So this is going to be a bit of a problem. So what I would like to do is I would like to address both of these issues. So what I'm going to propose is a way to resolve both of these issues, or at least try to alleviate them. So here's a second attempt. I'll say second, better attempt. So this is a pretty common way of doing this. So what we're going to do is we're going to use something called a polynomial hash code. Use a polynomial hash code. If you've heard of the word polynomial, that's what I'm talking about. Polynomial hash code. So just for the sake of clarity, I'm going to let string s be equal to c sub k minus 1, c sub k minus 2, c1, c0. So notice the indexing is backwards. You'll notice that when you're actually implementing what we're going to do here, this will actually be much simpler if you actually think about it later on. I'll advise you to think about it a little bit further. So you convert each one of these to a character. Sorry, you take each one of the characters, you convert it to what? An integer, right? So convert each character to an integer. And use these as coefficients. So those are those numbers that sit on front of the terms of the polynomial as coefficients of a polynomial. Now you might ask, Dan, what is this polynomial going to look like? So let me show you what it looks like. And I'm trying to tell you in advance, this isn't going to be too scary or anything, as long as you understand the main idea. So we have g of s, or g with input s. It's going to take for each one of these, it's going to take in It's going to take each character, cast it to an integer. It's going to multiply it by x to the power of k minus 1, plus it's going to cast the next integer, ck minus 2. It's going to multiply that by x to the power of k minus 2. And it's going to keep summing as the powers go down. And c1 times x to the power of 1 plus the last one where I converted to an integer. This will be when we have x to the power of 0. So this is what the polynomial looks like. Now you might ask, Dan, what is x? Now this is something that I can't tell you for every one of your applications, but I'll give you a suggestion for how you might go about this. So according to, if you look up the book on data structures by Goodrich et al., they give some suggestions. According to Goodrich, so Michael Goodrich et al., for a large English dictionary, so 50,000 words in it, they did a computer experiment, and they used some of these values here: 33, 37, 39, and 41. So they used these. So in their experiment, they would use some of these values for x, and they would build themselves a dictionary with the 50,000 words in it. So they wanted to figure out how many collisions would happen in that case. Well, what they found in their experiment, and so I'm going to paraphrase what they have in there. So they take the union of word lists provided by two variants of Unix. So you're using this 50,000 word dictionary. And then they looked at how many collisions would happen with these values of x. So in their experiment, they observed fewer than 7 collisions. Fewer than 7 collisions, which that's a pretty small number given the fact that the size of the dictionary, 50,000 words for their English dictionary. So that's much smaller. This is considerably smaller if you think back to some of the discussion we had earlier about arrays and linked lists in their worst case. So one other remark I want to make is that in the Java programming language, Java has for its string a hash code. So if you're curious about this, in Java, there's string dot hash code. So if you ever look up string dot hash code, what it does is it computes something just like this, where it uses x is going to be 31. So that's what x is for string hash code, is 31. So you'll notice it's quite similar to a lot of these numbers here. So these are some values you can try and practice and see if they match your application. So remember, like I said, this is from an experimental observation. So you must stress that you should, when you're building a hash table like this, when you're using your hash code, when you tailor your hash code for your application, you have to consider how you're computing it and how many collisions you're getting. So I recommend you try to measure this out a little bit more carefully. So you might ask, Dan, how exactly are we going to use this polynomial? Like, this looks a little bit complex at first, especially if you're not familiar with seeing things that look like this. So like, how do you do this? Now, all you have to do, now believe it or not, is there's actually another way to rewrite out this polynomial such that it uses half the number of multiplications. You can straight up compute that with a for loop. Just in the very similar vein as our first attempt at a hash code, except now you would have to have a running product that you're keeping track of, and you attribute that to a sum. You can actually rewrite that polynomial's expression in a different way using something called Horner's method. Now, I'm not going to focus much on that here, but what it does is it actually halves the number of multiplications that are necessary. It doesn't affect the big O, but it most certainly, in practice, will make an impact, because it literally, and this is, I mean this in the mathematical sense, it has the number of multiplications that are necessary to compute for a given string the multiplications necessary. So just to give you a flavor for what this looks like, so I'll let you think about this, and I encourage you to just pick a polynomial and try this out for yourself and see if this way of rewriting it makes sense to you. So what you could do is you could start off with the last two here. So you can take ck minus 1. So just for the sake of brevity, I'm not going to put the castings of the integers in here. So I'm going to have ck minus 1 times x plus ck minus 2. So notice that if I take this, and then I multiply this by x, it bumps up the power here from x to x squared, right? And then it multiplies this by x. So notice that I can then take the next term here, ck minus 3. I can multiply this by x. So notice that this multiplying by x to the result of this, because this is going to distribute appropriately, it'll bump up what would have been the result here if you carry this through. Notice that to bump up this x by 1 again, it'll bump that x up by another 1. So this will be x cubed, that'll be x squared, and that'll just be x. So you could keep going with this by rewriting it like this. But you'll notice that when I do this, I've already calculated out all of this first. So it means that every single time I would have distributed the x in that expression over there, I'm just going to calculate it later, which effectively will half the number. So you can keep doing this over and over and over again. So you could go plus. So after this, you could just have c2, then everything like this. You can multiply that by x plus c1. You can multiply all this by x, then you should have c0. So do you notice very quickly that there's that this actually, so the exercise I'm going to give you is to think about how, so just write out a polynomial as per the form we had over there, and then try rewriting it like this and see how many multiplications there are that occur. So count up how many there were. You should see that it's about half. If not, it is half. So when you stare at this, you might say, Dan, what if, like, I have to be a little bit more careful here, right? I can't just simply if I carry out some of these multiplications, what if the number gets really big? Like, keep in mind, we talked about the idea of that we want the integer to be large. But what if it's so large that it's like never going to ever have an impact on, for its magnitude, where it is in the table? Like, so it's so big that it isn't necessarily helping us progress to the idea that we're trying to spread the keys across the table. Instead, it's just getting too big, and we can't fit those numbers into registers on the computer. So when we have scenarios like this, we may end up with a situation called integer overflow. So this is a practical situation or an issue that in intermediate computations of this, we may have it where the integers start getting too big. And on a computer, those bits, there's a finite number of them. If you start exceeding that, it might, for example, reset the value of the integer. If it has, especially has a sign bit that dictates if it's a positive or a negative number, if it ends up being that it can flip the bit, which will happen if it gets too big, in addition, it will literally flip this bit, causing it to be an excessively large negative number. And then it may potentially sporadically start behaving in a way you don't anticipate. At least if you aren't carefully computing it out yourself. This is an issue of integer overflow. This is a serious issue when it comes to dealing with primitive types when you have big numbers. So usually we have some idea of how big the numbers will be. You try to allocate enough bits for the representation of that data type. However, if you're just using integers and you don't need the numbers to be too big, you can always use more bits. Or the other issue is that naturally the numbers could get too big and we get an issue called integer overflow, where what happens is the numbers get too big, it flips over, say a sign bit, for example, and then the numbers start getting really, really tiny. And then that's going to cause some unpredictable behavior when it comes to just, if you just wanted it to be like higher, it goes up, instead it'll start going down, and then it'll start going up, then it might start going down again. And when I say unpredictable, I mean from their expectations of a user. That's what I mean. So there's a great thing that we can do. So I'm going to actually incorporate the compression map into our hash code. And with doing this, this will actually fix our issue. Or at least it will alleviate the issue. I can't claim necessarily that it perfectly fixes the problem, but most certainly it will alleviate our issue. Especially if m is in fact a number that's going to fit in and the numbers don't get too unstably large. So this is something that can alleviate the issue. So we're going to apply mod or modulus or modulo for each iteration of Horner's method. So that you can think of what we're doing here as a variant of Horner's method. And you might ask, Dan, like, how do you know it's going to end up with the same number that you'd end up as a result of going mod m at the end? Well, this is the great part, is I'm not going to prove it here for you, but modulus has the ability to be preserved over multiplications and additions. So if you introduce all of these, it's no different than if I did it at the end. But the thing is, I'm going to, just for the sake of completeness, do it all here at once. So here's the algorithm. So I'm going to call it hash function, just to keep it simple. It's going to take in a string s and a value x. So you get to pick x. So this x might be, say, a constant that's in your class, say, if you're thinking about this in terms of C++ or Java or some other programming language. So the input is a string s, as we defined before, and a value x. So please take note of the ordering of the characters in their indices. So you'll see that you can actually rewrite this algorithm in a much simpler way once you realize this. So as output, it gives you a position for s in the hash table of size m. So it's going to give us a position. So I'm putting it all together now. So first I'm going to start off by assigning a variable val, the casted version of the first character. So that's what I'm going to first do. And then I'm going to go through a loop. So I'm going to go through the remaining characters. You're going to notice very quickly by the indexing, I'm actually sweeping from left to right. Although it looks like I'm reading this from top to bottom, or sorry, right to left. It's actually from left to right. Down to 0, we're going to do the following. So we're going to start at k minus 2. We'll go down to and include 0, okay? For each iteration of this loop, you're just going to update val to be val times x plus, you're going to cast the integer ci. So you're going to do this right here as per what we had up here. So notice each time this would just be embedded in each one successively. And you apply mod to this. Now you might ask, Dan, why mod? I'll answer that in a moment. Return val mod m. So just to be a bit more explicit, I just wanted to make sure you could see that the compression map is indeed being applied, as I discussed earlier. So just to be clear why we're going mod m, so why do we need that for our compression map? So why is the compression map mod m? Well, think about it. If I had, say, something like this. So if you've never heard of mod before, just think of integer remainder. So for example, if I take the number 5 and I divide it by 2, you'd get, how many times does 5 go into 2? It goes in twice. You end up with a remainder of 1, right? But notice how this behaves. So if I were to ask this same question for 6, well, you know that the answer in this case, 6 mod 2, well, If I take 6 divided by 2, I get a cleanly divided number. It's ended up being 3, but its remainder is 0. But notice that I can keep doing this. So 7 mod 2, I end up with 1. 8 mod 2, I get 0. And in fact, this causes what we call a periodic function. So what happens is each time I put in one successive number, it goes to the next spot, but notice that it never exceeds the number here that follows. So notice that it never becomes larger than 2. That's why it's capital M. So notice that if you started at 0, it'd be 0 mod M is 0, 1 mod M is 1, all the way up to M minus 1 mod M is M minus 1. But when you get M mod M, it becomes 0 again. So it's periodic. It has a period. So it forces you to go to one of the slots. So if you stare at this algorithm, you ask, okay, what's the time complexity for this algorithm? Okay, this first operation here should take you constant time, presuming we can access this in constant time. Then I go through each one of these. There's exactly k, well, there's big O of k many iterations here. So notice that in every time here I have multiplication and an addition with some cast in there with a mod with m. Now, presuming that modulus takes constant time, this all takes big O of k, many operations. And the last part here is just a modulo operation. So you can look at all of this taking in terms of time complexity, if we're keeping things simple, as big O of k for its time complexity. So think about this. If I have k, and k is a constant, so say I have strings, just like in our example of our application, where I had, say, 9 digits. Notice the length of the string would have length 9. That's a constant, right? So you notice that this will devolve down to big O of 1 in this case. So hopefully that is helpful. So if you want a more careful analysis, just take a look at the notes. So anyways, that's my discussion about hash codes. Are there any questions?